Hi, in this video, let's take a look at this Agilent 1731B LCR meter. This class of LCR meters, I believe, was released sometime back around 2009 or a little bit earlier, and had become the standard portable test instrument for LCR measurements. Dave Jones at the EEV blog did a teardown on both the Agilent 1733B and the 1733C back in 2012, and has some detailed account for the construction of these meters, which I'll put a link to that video down below for those who are interested. But I suspect although this is a 1731B instead of the 1733 series, the internal component layout is going to be largely very similar to at least the 1733B, which we'll take a quick look afterwards to check out. So one thing a lot of hobbyists ask quite often is that whether a dedicated LCR meter is necessary for project work. So the short answer is that it depends. If you are mainly building digital circuitry or simple analog circuitry, you probably can't get by with just a simple component tester like this one you can easily find on eBay. Or you can just simply use the functionality from your favorite multimeter, even though that most multimeters only have measurements for capacitors and very few have measurement for inductors. But if you're working with DC to DC converters or switching power supplies, having a dedicated LCR meter like this one may be necessary, as it typically specifies the accuracy within each range so you can trust the results. And before I open up the meter though, I thought I would do some simple measurements and show you what some of the common measurement modes and techniques are, and under what circumstances they might be useful. So the first component I wanted to measure is this 220 microhenry inductor. And let me power up the LCR meter and see how accurate it is. And I really don't like the sound. Actually, it sounds pretty horrible, but I don't know if there's any way to turn the sound off. Anyway, so let's take a look. So right now it's powered up and it is at a testing frequency of 1 kilohertz, and it is automatically set to inductor mode. So let's just hook it up without changing anything. Of course, I could have calibrated it, but it doesn't really matter. Right now, we just want to see how this thing generally works. And we can see the result, the reading is roughly 225 microhenry. So the first thing you notice is that we have two measurement modes. One is parallel, one is series. And right now we're in the series measurement mode. And if I change it to the parallel mode, let's observe what the readings are. So now we're in parallel mode, and as you can see that the reading changed a little bit, not a lot, but nevertheless there is a change in what we measured here. So this brings a question, whether or not we should use a series or parallel mode when doing measurement. Without going into too much details, here is the rule of thumb that we should remember. For the series mode, we usually use that to measure low impedance, meaning small resistance, small inductance, and large capacitance. And for parallel mode, we usually use that mode to measure high impedance, for instance, large resistance, large inductance, and small capacitance. And in this case, we are actually measuring a relatively small inductor. So in this case, we really should be using the series mode to measure that. So let's change it back to the series mode. And now the question again we have is what frequency should we use to measure the inductor or capacitor? Well, this is actually relatively simple. So for smaller component values, for instance, this 220 microhenry one, we can use a higher frequency like the 1 kilohertz right now we're using. And for larger inductors, for example, the transformer windings and or large filter caps, we usually use a lower frequency measurement. So again, we can show you that, for example, right now it's a 1 kilohertz, and now we can change the frequency to 120 hertz. And we can see that the reading here is 0.225 microhenry, which is exactly pretty much the same as we had before. Now, of course, we need to be very careful. As I mentioned, this is a relatively small inductor here, so we're using the series mode to do the measurement. Now, take a look at what happens when I change it to parallel mode, when the measurement frequency is 100 hertz. And you can see that we no longer get the correct reading. Right now we're reading 1 point some millihenry, which is definitely incorrect. So this is kind of the pitfall that we need to keep in mind, is using the appropriate frequency range, using the appropriate frequency and the appropriate mode, parallel or in series, to measure the specific component that you're using. Now, if you read some of the data sheets and some components are specifically mentioned to be measured under a specific frequency in a specific mode. So generally, if you have the manufacturer's instruction, we need to follow that. Otherwise, we just need to keep in mind that when doing serial mode measurement, we are measuring low impedance. Again, it's small resistance, small inductance, and large capacitance. And when doing the parallel mode measurement, we're doing a high impedance measurement, large resistance, large inductance, and small capacitance. And I just want to show you also how the frequency, measurement frequency, affects the measurement result here. So now this is a relatively small inductor, so now let's change it to a larger one. So here I have a very large winding, and so let's take a look at inductance, shall we? So now we're showing roughly 750 millihenry between the white lead and the black lead here. And now the frequency is 120 hertz. Because this is a relatively large inductor, we can use the parallel mode. And now we're showing that is 770 millihenry here. And of course, the measurement also is dependent on the frequency you're measuring it under. So right now it's 120 hertz. If we change the frequency to 1 kilohertz, let's take a look at the measurement. And as you can see that the measurement result changed significantly. And again, typically you need to follow the manufacturer's recommendation on what frequency to use for specific type of component. And for this relatively large inductor, we usually use the low frequency measurement. So that is something just wanted to point out. And of course, as I mentioned earlier, if you have a component tester and your requirement is not that stringent, then you can easily use a component tester to check out the component at hand. So for this 220 microhenry inductor here, let's take a look here. And it's showing 0.21 millihenry and with a series resistance of 0.4 ohms, so it's not too far off. Nevertheless, we don't know the exact condition this component is measured at, so that's why we need a meter like this Agilent U1731B LCR meter. Oh, I forgot to mention that you can also use the LCR meter to measure the quality factor of your coil or an inductor here. So let me hook back on the 220 microhenry inductor here, and we change the frequency to 1 kilohertz. And now let's take a look at this button labeled D or Q, so it's a dissipation or quality factor. And for inductors, the most useful display would be the quality factor. Of course, the quality factor and the dissipation, they're just reciprocal of each other, so knowing one would automatically be able to calculate the other. So now we can see that the quality factor of this inductor is not particularly high, but it's at roughly 3.8. So what I'm going to do next is to measure the capacitance of this electrolytic capacitor here. And this one I have here in my hand is a Nichicon 1000 microfarad capacitor here. And it is relatively large in value. So we will change it to capacitance measurement mode, and we'll leave it at 120 Hertz because of the value we're trying to measure. And remember also, we mentioned earlier that for larger capacitance, we usually measure the capacitance in series mode. So now we're going to change it from the parallel to series. And with that all set, let's hook it up. And even though this is polarized, it doesn't really matter which lead goes where, because this is essentially using a very, very low magnitude sinusoidal wave to drive this capacitor here. So the polarity doesn't matter. Now let's wait till it settles. And it's at 994, 97, and it changes a little bit, but nevertheless, it is roughly 1 millifarad, and which is exactly what we were expecting. Of course, one important feature of any LCR meter is the ability to measure the equivalent series resistance. And so let's see how we do that here. And as we have seen earlier, this meter has a dissipation and quality factor measurement. So unfortunately, it doesn't have a direct equivalent series resistance measurement mode, but the dissipation factor and the equivalent series resistance are related in that the equivalent series resistance equals the dissipation factor times the reactance of the component under test. So for this 1000 microfarad capacitor here, let's take a look at what is our reactance. So the reactance calculates as 1 over 2 pi f c, right? So let's do 2 times pi times the frequency, which is 120 Hertz, times the C, which is our our capacitance, which is 0.001 farad, because it's a 1 millifarad, and we shifted by another 3 decades here. So the result is 0.75. Of course, we have to take the invert of this, because it's essentially D times XC. XC is 1 over 2 pi FC. Okay, so now let's invert this. And now we times the 0.066. So the result is your equivalent series resistance, in this case, is right under 10 milliohm. So let's take a look at the measurement using our this component tester here, and we will unclip this, and oops, let me bring it up here, and let's take a look. And as you can see, that the value here, it's a little bit off, right? So we have this roughly 1000 microfarad value, which is correct in the ballpark, but the ESR is a little bit off. Of course, different meters have different ways of characterize component values, but since we don't know exactly how this is calculated, so we can only take in the value at its face value. And we can definitely do things comparatively, compare this specific capacitor with another capacitor, but we cannot get the absolute value we're trying to derive. Whereas using a proper LCR meter, you can get the value you need. Of course, we didn't zero out the readings before we did the measurement because it's such a large capacitor, and it didn't really matter. Now, of course, if you want to do precision measurement, you really need to zero out your meter before doing so. So how to do that? Well, let's demonstrate that using measuring this precision resistor. This is a 100 ohm, 0.1%, so it's very precise resistor here. So let's take a look at how to do the resistance measurement using this meter. So for that, I'm going to change it to resistance measure mode, And in this case, the frequency doesn't matter that much unless you are measuring a wire wound resistor, which you wanted to make sure that the frequency is low enough so it doesn't add in any inductance here. And so to measure it, we need to do some calibration. So for that, we wanted to press this cal button. And it says it's open cal, but we actually first need to change the mode to the specific range that we are interested in. So it's a little bit not quite intuitive the way this meter works. So let me press this. Right now it's in O mode, so that looks right. Let me just see how is it. Yeah, this one actually, because the first one is ohm to roughly 2 ohms, and this one is 200 ohm. So now let's zero it out. It's a short. So now I need to press the cal. And now it's calibrated. So now, as you can see, that with this 2 leads shorted, it's showing 0 ohm. So now let's place in this resistor here, and we'll see what the values we get. And it's a 100.01, so it's definitely well within the tolerance range of this 0.1% accuracy resistor. Another thing I wanted to point out is the use of this guard terminal. And let me explain when you might want to use this, in case you are wondering. So a couple of years ago, I made a video explaining why guarding is needed in low-level measurements, specifically when using an electrometer. In essence, the guard holds the potential at the same level as the signal, thus preventing any leakage current flowing from the signal-carrying conductor to elsewhere, most likely the ground. So let me draw that and to make things even more clear. And for instance, here is our signal-carrying wire, and here is the ground, right? So when this wire is long, we have this straight capacitance distributed everywhere, so that when you are looking at the port at the other end, you will see this whole thing as capacitive. And if you were to measure a capacitor here, you're going to be adding on to the actual capacitance all the straight capacitance on the wire. And this is fine, you can always null it out, but if the wires are long and you are moving around, and so this straight capacitance changes from time to time, and it will prevent you from making a valid measurement at the other end. So let's take a look at what guarding does to this situation. So let's ignore this drawing up here. Let's do it underneath here. So again, we have the signal here. And then, instead of the naked signal wire, we have a guard that is surrounded by around the signal. So this is a guard. And again, we have this ground. So in essence, the guard is held at the same level as the signal wire. And so there's no current flowing between the guard and the signal here. So there's no current flow. Whereas here, in our previous example, the current flows readily from the signal wire to the ground. And thus, the signal flow is actually what constitutes as the capacitance here we're seeing. So because there's no signal flow between the signal and the guard, and there's no capacitance here. And the current flowing from the guard to the ground is actually not counted in terms of our measurement. So from the signal point of view, there is no leakage current, and thus there's no straight capacitance. So let's take a look at this in action, and we'll understand this a little better. So for this experiment, I'm going to exaggerate things a little bit, and these leads are nice and short. That's the exact reason they don't want to add any straight inductance or capacitance to the measurement. But now we're going to swap them for a much longer leads. So, and also for us to be able to visualize this, I'm going to put this on capacitance mode, so you can kind of read what the straight capacitance is. Now we're in capacitance mode, and right now it's just 4 picofarad. It's really nothing. And if I remove these leads, we should see that drop a little bit. And so now, let me put on some really long wires here. So these are the very long alligator clip wires, and we can put it on. And you can see that depends on how we're positioning these wires. The straight capacitance could range from just above 15 picofarad, all the way to, if I kind of bunch these together, to 30s and maybe even higher. And it depends on how tightly these are coupled. So clearly this is a disadvantage if you're trying to measure, say, a capacitor the size of 10 picofarad. Of course, you can null it out, but the point is, if you are moving these wires, right, so this measurement is going to be all over the place. So the measurement will not be accurate, even though right now we can see that it's 29, 30, so you have no idea how large the actual capacitance you're trying to measure is. So the point here is that in this situation, you wanted to use a guard. And for an LCR meter like this Agilent U1731B, you can usually buy a text fixture that includes a guard terminal, and you can use that to do some precision measurement. But here we're gonna make our own guarding device so that you can see how exactly it works. So in fact, it's quite simple. What I did here is I'm using this BNC connector here. And if you look at the green wire is connected to the outer shielding, which is the ground, and the red wire is connected to the signal. So what I'm going to do is basically going to connect the guard to the outer shielding of this BNC connector, and the signal going to be swapping this red lead with the actual signal wire to the center of the BNC cable. So that's what I'm going to do. So now I'm going to unplug this cable, and you can see that the capacitance measurement dropped back to the nominal 3.6 picofarad, which is the residual capacitance. So now I'm going to plug in my guard and the actual tip of the BNC. Of course, now the capacitance increased a little bit because these wires are still have some length and straight capacitance, but that's not what we're going to worry about. So to do the actual testing, I'm going to connect to this really long BNC cable to this guard terminal. And in theory, it should not affect the capacitance that much. And as you can see here, well, it does increase the capacitance a little bit, but it does not increase it significantly. And that's because the guarding terminal is held at the same voltage potential as the signal. So to actually see that, let me just show you on the oscilloscope back there. And I powered up the oscilloscope, and we can hook up the probe here. So let's see here. So I'm going to put the negative of the probe to the negative terminal here. So just want to show you here. I'm going to plug it right here, and so I'm going to probe the BNC tip, which is remember the signal wire is this red alligator clip here, and you can see that we have this periodical sinusoidal wave, which is very, very small in magnitude, which is our test signal that is applied to the device under test. And if I take a look at the shielding of the BNC, which is now connected to the guard terminal, you will see the similar signal waveform here. Whoops, I don't want it to, now it just turned off. And this is another annoying thing, is it doesn't stay on very long. So now let me go change it to capacitance measurement mode again. Okay. So now that's our test signal. Basically, this is to illustrate that the guard is held at the same level as the signal here. So now we can use the setup to measure our 10 picofarad capacitor as before. And again, I'm using the negative, which is this alligator clip, to clip it to the one leg of the capacitor. And the other side, basically, I'm only going to use this center pin, which is the red terminal coming from this positive input. And the guarding terminal, I just leave it floating. So now you can see that we get a much more accurate capacitance reading. And perhaps the most important part is that the residual capacitance is fairly stable. Instead of like before, when we move the wires, it changes quite a bit. Here it actually doesn't change that much. So this is why we need the guarding when making this kind of a small capacitance measurement, and that makes it much more accurate. And this is because the guard potential is held at the same potential as your signal wire, so that there's no current flowing between the guard and your signal, and thus preventing the straight capacitance getting into the equation of our capacitance measurement here. So now we have covered all the basics. I do want to open it up and take a brief look inside to see what the construction is like. And as I mentioned earlier, this one probably is exactly the same, almost identical to that in 1733B. So now let me remove the case. Let me switch the camera angle a little bit so we can see it a little better. And as we expected, the internal looks pretty much identical to that of the 1733B that Dave Jones did a teardown with. And of course, it's a little bit different than the 1733C, which was a newer version. Now we have this TLC 7135C, which is a 4.5 digit ADC here. And then we have a Escort branded chip, which is the main processor, and I don't have much information on that chip, but I think it might just be a 8-bit microcontroller with some integrated LCD driver. And then everywhere else we can see some of the MOXes, and these are the which by the way I'll put on high resolution photos on my website, but you can't probably see these. Some of these are, for example, 4052s and 4053s, and then we have a bunch of op amps and all over the place. And interestingly, what they're using is they have TL071, 82, and 62. I can see quite a few all over the place. And on the input side, we have this glass fuse here, and we do have a mauve, looks like, by the look of it. And here, tucked in, is a, you can't see the marking here, but this is a Holtec HT7660, which is a DC-DC converter, which makes sense because the ADC chip here requires both the positive and negative supply voltage. So we have this DC-DC converter tucked in right here. So all in all, this is what is inside this U1731B. And as we expected before, this is not too much different than some of the newer LCR meters in the same series. And that pretty much concludes this video. I hope I have clarified things a little bit and you have learned something new. If you liked the video, please remember to like it, give it a big thumbs up, and remember to subscribe, share. I will catch up with you next time.